Good morning, good afternoon, or good evening. This is a continuation of the Step 2 2024 paper walkthrough. We are now on the applied questions, and it's all about drawing that really accurate picture. As always, before watching this video, you should be having a go at the questions yourself, and either now be watching to see if there was anything you missed about the problem, seeing other ways to tackle the problem, or if you've had a go and got stuck, looking for some hints for you to pause the video and then try on your own solution. So we're now on question 10, another mechanics problem. So our first thing we need to try and do is understand the situation and therefore draw a accurate large picture. So question 10. A triangular prism lies on a horizontal plane, so some kind of flat space. Again, I'm not entirely sure yet whether I want to draw the triangular prism vertically, whether I want to draw it on one of its sides, or if I even want to draw the picture in 3D, or just look at it down a cross section and pretend it's really a 2D situation. One of the rectangular faces of the prism is vertical. The second is horizontal, and the third oblique rectangular face makes an angle alpha with the horizontal. So we've got some kind of triangle as so. One being horizontal and vertical, it is telling us that it is right angled. So we have some kind of shape that looks like this. Again, I'm not sure whether I want to draw it in 3D or if I want to look straight on, so it basically looks only like a triangle. But that's the shape I'm dealing with. The two triangular faces are right angled and are vertical. Nice. The prism has a mass of m and it can move without friction across the plane. So when I do end up putting it on this surface, there'll be no friction. I'm just going to put a little mu equals 0 down on the side to remind me of that fact. A particle of mass m lies on the oblique surface. So there's going to be some object on this face here. The contact between the particle and the plane is rough, so I do have a coefficient of friction. And now we need to start dealing with some stuff. Okay, nothing about this appears to have any motion in these directions. It appears that certainly if you put an object at rest on a surface, it's going to fall down the line of greatest slope. So I think when I'm drawing the picture above, I am going to look directly face on and keep it simple in a 2D style. So I'm going to have my prism side on as so, with the angle there alpha, and then my object, my particle, is going to be here. I've got my mass of m and my mass of m. Maybe a little small for my liking, but we may redraw that picture later on, zooming into what's important. Okay, we've also been told that the coefficient of friction here between these two is mu. And now we need to think, if mu is less than tan alpha, the system cannot be in equilibrium. Okay, well, firstly, let's break down what could go wrong. Apologies. What could go wrong in this situation? We could have this particle sliding down this face here. That would be a very simple way for this to break. We could also actually have, and if that does slide down, this wedge, this triangular prism, will actually start moving backwards. As that m slides down, it's going to have some forward-ish momentum, and that forward momentum has to be counteracted by imparting some backward momentum. Now, officially, momentum is a further mass concept, so shouldn't be needed in a problem like this, but there's nothing stopping us using it if it turns out to be a good problem-solving technique. But the most obvious way that this situation could fail to be in equilibrium is that smaller particle sliding down the slope. So let's set up and see if I can model this smaller particle and what that will involve. So on the smaller particle, we're going to have a reaction force perpendicular to the contact surface, and we're going to have the weight acting directly down. We do have a rough surface, so we also have a frictional force going back up the slope, opposing that potential down the slope sliding. So now let's just do our normal set of force work. On that smaller particle, I'm going to go perpendicular first. Perpendicular, there is absolutely no way that there is motion. So then R equals, let's put my other angle in. Let's try and be consistent with my color coding here. So that angle there is alpha. Once you've justified to yourself that once, you never really need to justify it again. But some simple angle chasing tells you that angle's alpha, so therefore the R going away from the slope is equal to the mg cos alpha, the component into the slope. Okay, well now if I look parallel to the slope, now we can't assume equilibrium, so I'm going to now look at let's try and find out the resultant force. And if the resultant force is positive, then, or non-zero, then we can't have equilibrium. So the resultant force going down the slope is going to be mg sine alpha is going down minus the frictional force. So this is mg sine alpha, but the frictional force is mu r. Well, officially it's great. The frictional force is less than or equal to mu r because we're subtracting the reaction force. The resultant force, therefore, is greater than or equal to mu r. So that's mg mu cos alpha, as friction is less than or equal to mu r. But this thing we can be a little bit clever with. We've got a common factor of mg, but I'm also going to pull out a cos alpha, because pulling a cos alpha out of sine alpha leaves behind sine over cos, or tan, minus mu. But mu is less than tan, so tan minus mu is greater than 0, so this thing is greater than 0, as mu is less than tan alpha, which means, so this is Newton's first law, which you very rarely actually quote. So Newton's first implies it's not in equilibrium. You see an object at rest or at constant speed, the conditions for equilibrium, cannot have a resultant force. We have a resultant force here, so we're not in equilibrium. Lovely, that's part I done. Let mu equal tan lambda. So I'm now picking out a particular value of mu, and because tan is what we call an order preserving function, because lambda is less than alpha, tan lambda is less than tan alpha. So we are not in equilibrium. So we now have we have a motion. So this object is indeed going to start moving down the slope. A force P is exerted on the vertical rectangular face of the prism, perpendicular face, directed towards the interior. So I'm putting a force here, P, perpendicular to the face and directed towards the interior. The particle and the prism accelerate, but the particle remains in the same position relative to the prism. Interesting. So this particle here is going to look like it's stationary. Now it's not stationary because the whole system is moving this way, but it's going to look stationary relative to the plane. Okay, well, what does that really mean? Well, that means that they share exactly the same acceleration. If they don't move relative to each other, whatever the acceleration is on the big prism, that's going to match the acceleration on the smaller object. Okay, show that the magnitude of the frictional force between the particle and the prism is given by that. Okay, so I'm going to subtly change some of my notation here so that it matches their notation. They're now saying capital F is their frictional force. And if I read a bit further, find a similar expression for the magnitude of the normal reaction force between the particle and prism. So they've called this N. And if I fill in the rest of the forces on my large prism, I've got a capital mg going down, and that contact force is the force of the prism on the particle. So there's an equal and opposite for the particle on the prism. Okay, and now, but for a similar reason, we have another frictional force, this time on the prism. There is a frictional force on the particle holding it back up the slope, but that means there's also going to be a frictional force pushing down the slope on the prism itself. Both applications of Newton's third law. Now this causes the situation to be quite awkward with all of these different paired, or both of these two paired forces, which normally get called internal forces, but that means we can ignore them if we look at the entire object as one single object, having the particle and prism combined together. In that case, both of those F's will cancel each other out, both of the N's will cancel each other out. So let's do as so. So the entire system, if I treat it just as one object, then the total horizontal force, well, it's only P. The only force pushing this thing forward is P. I have forgotten to add in the contact with the ground force, which I'll put in there. Now that's a vertical force, it's not affecting my horizontal motion. So P is equal to the total mass times A. So that's going to be a really nice way to cancel out this acceleration in a later part of the problem. Okay, so now let's look at just the particle. The particle, if we go horizontally, we're using an F equals ma. My horizontal forces, now I'm having to go horizontally, not parallel or perpendicular to the plane, to line up with the acceleration. So let's try and put our angles in the right place. That there is an alpha and that there is an alpha. So we get, horizontally, we get n sine alpha minus f cos alpha equals little ma. We're only modelling the little particles, we only use the little m. And if we also do up equals down, there's no motion up equals down. So the f sine alpha plus the n cos alpha is going to equal the downward force of mg. Okay, well, I know how to get rid of the A. I've got that from the totality, the total system. So at some point, whenever I choose, I can replace the A with P over M plus M. Do I want to do that yet? Maybe. But I do want to get rid of the N. Now I've got lots of choices here. I could try and rearrange both to make them both N equals. I actually, you may recognize this as a very common style of simultaneous equation between, well, normally it's between a R and an angle, but we can rearrange both of these to make, well, the first one you can say n sine alpha equals f cos plus ma, and the second one, n cos alpha, is mg minus f sine a. And if I square and add, I can get rid of the alphas. Or if I divide, I can get rid of the n's. Now that just actually feels like more work, because then I'm going to have a fraction equaling tan alpha. If I look at my answer, there is no tan alpha involved. So although that looks like quite useful, don't think I'm going to follow through on that technique. So instead, I'm going to call these equations 1 and 2 and just do our normal thing. I'm going to multiply equation 1 by cos alpha. I'm aiming to get the n terms the same. So that's going to be n sine cos minus f cos squared equals ma cos. I'm going to multiply the second one by sine alpha. So that's going to be f sine squared plus n sine cos equals mg sine. Now there's some things which are really promising here. I can see the mg sine. Well, I can't really see that in the answer here. I've got a g sine, but then I've got a bit more than just m, although there is an m on the outside and the other factor does cancel. So I do have the mg sine alpha being that first term, and the second term, the cos alpha, well, that's with the a, which is what brings us in the force P. So now if I subtract these two equations, I kind of want to do the subtraction in the opposite order to the second one, subtract the first one. That's going to give me f sine squared plus f cos squared. Oh, a classic sine squared plus cos squared. And if you did follow through with the other method, you'll probably get a similar thing. And that's going to equal, I'm doing the second minus first, mg sine alpha minus mp. I'm putting that capital, that little a in, cos alpha. So then that's f equals, factorising as they've done, and I've typoed in the denominator there, m plus m, open the bracket, that leaves m plus m. An interesting choice of how to factorise this. We're introducing an m plus m bracket on the sign, which, is that a good idea? Maybe it'll come up later on why we want to factorise in that way. But there you go. That's our expression for f as given. And find a similar expression for n. Now I almost feel like I don't want to sub this f. I don't really want to put this f back into one of these. I rearrange because that f is just so unpleasant. I think it's what I'm going to do, is do this whole thing, but cancelling off the f terms instead of the n terms. I think that might actually be simpler. So I'm going to take equation 1 and times it by sine alpha, the opposite of what I did before, minus f cos sine equals ma sine, and then times the second one by cos, giving me f sine cos plus n cos squared equals the mg cos. And now if I add these two equations, cancelling the f terms, we're left with n equals, I've jumped the step of the sine squared plus cos squared, equals, now I could try and jump more steps here, but that feels a bit too brave. So I'm going to go just a tad slower. So putting the a in to that first one, I'm getting mp m plus m sine alpha plus mg cos alpha. And just because this is what the question did on the other one, I'm going to do the same. This is m plus m g cos plus p sine. So I've now got n and m in very similar looking forms, very symmetric actually, in the way that they're written. Not really surprising. They are near equivalent in, we're just doing horizontal and vertical forces. Okay, part 3. Hence, show that P must satisfy that expression. Okay, so now we need to put some inequalities on some of this stuff. And notice actually we've not included this lambda at any point in the question. We introduced mu equals tan lambda, but didn't actually use it in the previous part. So how does this mu come in? Well, this is directly from the definition of coefficient of friction. F is less than or equal to mu n. Now, normally we use this as an equality, F equals mu n, but that's only if there's motion or limiting equilibrium. Now, you can argue that this particle is in motion, but it's not in motion relative to the surface of which the friction is acting. And therefore, we don't actually have equality here. This friction could actually be quite a lot less. It doesn't have to have hit its maximum possible value. And now this is quite a nice equation because now we can just sub in all the stuff we know. And I'm going to immediately cancel the coefficients, the m over m plus n. So the f is this thing, and that's less than or equal to m plus m g mu cos alpha plus p mu sine alpha. Now this looks like it might be giving an upper bound. Depends how I rearrange all this, but I kind of want to throw that way to keep things positive. So I'm going to do that. So then this side can be m plus m g. It was a sine alpha. I'm subtracting a mu cos. And that's going to be less than or equal to the p cos plus mu sine. Okay. Now I should be a little worried because I want to divide by this thing. Could this thing be equal to 0? Well, I hope not, for one. That would make the question quite annoying. But that thing would equal 0 if tan alpha mu equals -1. But alpha is between, well, alpha's less than pi by 4. So tan alpha is certainly positive. Mu is, coefficient of friction, is also positive. So this thing cannot equal 0. Should probably put a bit more of a justification on the side for that. So P therefore is going to be greater than or equal to m plus m g sine alpha minus, I'm going to put this back in as tan lambda, as we've been told that's what it is, plus, even after saying that I didn't do it for that second one, sine alpha. Ooh, now that's an ugly looking expression. But we know what we're aiming for. We're aiming for a tan alpha minus lambda. Well then, let's make this look like tans. And if you are confident with your addition formula, you'll already be able to see that this looks very much like an addition formula. So I'm going to divide top and bottom by cos alpha. So this is going to look like tan alpha minus tan lambda on the top. The bottom is 1 plus tan lambda tan alpha, which is exactly m plus mg tan alpha minus lambda. So we've got P's lower bound. P has to be greater or equal to that thing. But now how am I going to get P's upper bound? Now notice that P's upper bound is very, very similar, except it's got a plus here. So that will mean that this will be a plus and this will be a minus in the inequality. It's kind of going back and seeing if I can see where all these things would have changed. That thing would have been the plus, that would have been the minus, then the plus and the minus. Did that come from somewhere sensible? Maybe. Now, neither of these new expressions are actually something we've dealt with already. So only some of the stuff has swapped signs. But actually, the whole picture could have been slightly different. And if we think about the mechanics of the situation, we currently have a lower bound. So that's if P is quite small. If we're pushing this quite small, then we're expecting the block to be wanting to slide down the slope. We're not going too fast. But if we made this P really, really big, then actually the block would almost be sliding up the slope. We've got so much pushing force behind it, then the block is going up the slope instead. So this F is actually now pointing down the slope, not up the slope. So we actually have two different situations. And maybe we should have been worried about that for the rest of the problem. Because really there were two situations that we should have dealt with the rest of the problem. One where the F was pointing up, one was where the F was pointing down. Let's see if we can kind of posthumously deal with that. But certainly there's going to be a lot of forces which are now going to be in opposite directions. I feel like I need a new picture, so I'm going to jump to the next page. I'm now going to redraw the picture, now assuming that this P force is quite large. So we've got a large P, which means the frictional force is now going down the slope. Our reaction force is still up the slope. We still have this mg. And let's see what that means for the problem now. So we still have, on the whole system, we still have that P equals m plus ma. We have on the particle going horizontally. Now this is still going to be the same, isn't it? Let's put my angles in. The angle there's alpha. This angle here is alpha. This angle here is alpha. So horizontally, I'm getting F cos plus, now this is a plus now, plus N sine, sorry, there you go, caught up with myself, equals MA, and vertically, this is now N cos equals, I'm actually going to put this as N cos minus F sine equals mg, so I can better compare it to my other equations that I had before. Because I could go ahead and solve these again. I don't really want to, because I've already solved them once, and that was a little bit of effort. So I want to compare them and see if I can just say a bisymmetry. So we'll notice, and I'm looking at these two equations here, that in both cases we have the positive n sine, but the f term has swapped. And on the second one, we have the n cos, but the f sign has swapped. So in both cases, well, the magnitudes therefore are just equal. The solution the F force would be just the opposite sign of my answer. So a kind of bisymmetry. The F is going to be exactly what we had before. M plus M G sine, but that's going to be with the negative sign plus P cos. And N is still going to be the same as what we had before, which was everything positive. So that's M plus M G cos plus P sine. So the situation is identical, which is also why the question says show the magnitude of F. It's kind of subtly pointing us in the direction that F could have is actually two different values, potentially two different values, depending on the direction. So now if we set up the same thing, so now F is less than or equal to mu n. And if I do the same thing, but now I've got a sign swap, maybe that will be exactly the sign swap that's needed in the inequality. So this thing is less than or equal to m plus m mu g cos plus p sine. There's a mu in there somewhere. Okay, yeah, we're going to have the sign difference now. And now we're looking for an upper bound. So I want to put P on this side. So that's been cos alpha minus mu sine is less than or equal to the m plus m g. And then on this side, I've got now sine plus mu cos. So that's P is less than or equal to m plus m g. And we're going to basically have exactly the same situation again. Got the sine alpha plus tan lambda cos alpha over cos alpha minus tan lambda sine alpha, divide top and bottom by cos alpha. And now we're basically home and dry. Tan alpha plus tan lambda. Have I swapped my signs anywhere yet? Nope, I've still got the right signs. 1 minus tan lambda tan alpha, which is m plus mg tan alpha plus lambda. Thus, we can write our conclusion. The m plus mg tan alpha minus lambda is less than or equal to p. That's what we got on the end of the last page. Is less than or equal to mg tan alpha plus lambda. Squeeze it in as required. Quite a nice little problem there in the end, certainly with having to spot that there was an alternative. Depending how big P is, it could either be force, or it could either be having the particle sliding down the slope or attempting to slide down the slope, or the particle attempting to slide up the slope if we were pushing hard enough. Which it does make sense if you ever put a ball on a ramp and you push the ramp, the ball might roll down if you're not pushing the ramp fast enough, or the ball will roll up. Not really how fast, but rather the acceleration that you're applying to the ramp. Nice little problem. Again, making it really obvious how much a good pitcher is essential. And in this question in particular, the subtlety of the frictional force being up or down the slope. Hopefully you found that problem, that work through quite useful, quite insightful. And keep an eye out on the playlist for all the other questions on this paper.